Welcome to video number 2. We're going to continue our discussion of autoionization. And so far, we've only been talking qualitatively about this process. And all we really know is that water creates ions. So we want to talk about it quantitatively and measure exactly how much. So let's take a look at our equation again. We have H2O creating H plus and OH minus. And what we want to know is how many ions are we creating. So in order to know how many ions I'm making, naturally I want to know how much water I started off with. So in order to standardize this process, I make a set of initial conditions. And I say, okay, I'm going to measure the amount of ions that I'm making for 1 liter of H2O. The second thing I want to standardize is the temperature. Because the temperature can affect the extent to which something reacts, I set a given T and make all my measurements after that. That temperature is usually 25 degrees Celsius or 298 Kelvin. Once I measure the amount of ions that I'm making for 1 liter of water, amount of ions that I'm making for 1 liter of water, what I'm going to do is I'm going to set a constant. I'm going to make a constant. And in that constant, I'm going to make a ratio of the amount of ions that I'm making, which is the products, compared to the amount of water that I have, which is the reactants, or in this case also we have 1 liter of reactants. And what I'm going to do is I'm going to set a ratio comparing these two things. So I'm going to make a ratio of the products, which is basically the amount of ions that I'm making, again, over the ratio, over the concentration of the reactants. And if you really think about it, this is a really ingenious way to instantly know how much of any compound is being created. Not just for this reaction, but for any reaction. So if I see a high K now, for example, I automatically know that that's due to the fact that I have a lot of product. And if I see a low K, I automatically know that it's because I don't have that much of product. So let's figure out our K. So like I said, K is calculated by the concentration of the products and the concentration of the reactants. And just to clarify, the reason I'm writing it in brackets is this brackets mean the concentration. And so that's what we're looking for. We're after the concentration of the products and then the concentration of the reactants. And we're measuring the concentration in moles per liter, or also known as molarity. So the good thing about calculating this K for water is that we don't actually have to do any lab measurements because they've already been done for us. So for 1 liter of water at 25 degrees Celsius, there is 10 to the negative 7 molar of H plus. So remember, this is part of the products, that's why I'm putting it on top. And there is 10 to the negative 7 molar OH minus. So now the only thing I need to figure out my K is actually the concentration of H2O. And I do know that I have 1 liter of H2O, but I want my I want my concentration in molarity. And I won't go into the math of how you get the molarity of water, so you'll just have to trust me and accept the fact that it is going to be 55.5 molarity. And if you do the math, it comes out to 1.86 times 10 to the negative 16. So ordinarily we would stop here, and this would be our K, and we would be done. But the autoionization is different. So if we look at our water equation again, if we look at our water equation, again, we'll see that some of the reactants, for it to convert to product, some of the reactants have to convert to product. So the amount of reactants that I started off with initially is not what I'm going to end up with in the end. So to figure out my true K, what I would have to really write, and ordinarily I have to write this for my other K's, is again the concentration of the products, which I know, and the concentration of the reactants initially, I'll just say initial, minus the concentration of the products. This would be a true reflection of my K. But as you can see, we didn't do that in our example. We just left water as is. And why is that? The reason is because the concentration of the ions is so low that it practically has no effect. So, and we can prove this if we look at the ionization. The concentration of the ions is 10 to the negative 7 molar. So it's 0.0000001. And the concentration of H2O is 55.5 molar. So even if I were to do a precise calculation and were to subtract the ionization from the reactants, it would be 55.5 minus 0.00001, and you can see that my answer in terms of significant digits is practically unchanged. It's 55.5. So I like to think about it as if you take a bottle of water to the ocean and you fill that bottle of water with ocean water, it will not reduce the amount of ocean that you have. So just like that, we don't think of ionization as reducing the amount of water that is available. So what we do here, so if we go back to our equation, so what we would do with the ion product of water is take this 55.5 molar quantity, and what we do is we multiply it with our K that we got initially. So what we end up getting is 10 to the negative 7 molar times 10 to the negative 7 molar equals to 55.5 molar times 1.86 times 10 to the negative 16, which all really just equals to 10 to the negative 14. And we have a new K, which is known as KW, or also known as the ion product of water. And this leads us to the golden rule, is that since this is a constant, KW, no matter what, always 10 to the negative 14th at 25 degrees Celsius. And you'll see the relevance of this in the next video, and you can see how to apply it.